In this video, we'll study source and derivation of elliptic integrals, and we'll also solve complete elliptic integrals of first and second kind. Now, mathematicians for long have been fascinated by arc length of an ellipse. So while they were trying to find out arc length of this ellipse, they came across certain integrals which were then called elliptic functions. Over a period of time, these elliptic functions are now called as elliptic integrals. So what we'll do is we'll write an expression for arc length of this ellipse. Now, since this ellipse is symmetric about both x-axis and y-axis, we'll find arc length for this section. Now we know that parametric equation of an ellipse is x equals a cos theta and y equals b sin theta. Now dx upon d theta is minus a sin theta and dy upon d theta is b cos theta. Now we can write this length as 4 times and then this arc length integral under root of dx upon d theta square plus dy upon d theta square into d theta, where theta varies from 0 to pi by 2. So it'll be this 4 times and then from 0 to pi by 2, and this is under root of, now dx upon d theta is minus a sin theta. So it'll be a square sin square theta plus dy upon d theta is b cos theta. So there will be b square cos square theta d theta. Now we can write a square sin square theta as a square into 1 minus cos square theta. So now it will be 4 times this integral from 0 to pi by 2 under root of a square minus a square cos square theta plus b square cos square theta d theta. Now we can write this as 4 times this integral from 0 to pi by 2 under root of a square plus b square minus a square into cos square theta d theta. Now in ellipse we know that b square is a square into 1 minus e square. So basically we can write b square minus a square as minus a square e square. So we'll get this length as 4 times 0 to pi by 2 under root of a square minus a square e square cos square theta d theta. Now we'll take a square out. So now we can write this as 4a into this integral from 0 to pi by 2 under root of 1 minus e square cos square theta d theta. Now we know that in definite integrals, this integral from 0 to a fx dx is this integral from 0 to a f a minus x. So we can write this L as 4a and then this integral from 0 to pi by 2 under root of 1 minus e square and then cos square, and here it will be pi by 2 minus theta d theta, and cos pi by 2 minus theta is sin theta. So we get this integral as 4a into this integral from 0 to pi by 2 under root of 1 minus e square sin square theta. Now this integral, it is called as elliptic integral, and it is not possible to solve this integral analytically. So from arc length, we get this integral which is 4a from 0 to pi by 2 into under root 1 minus e square sin square theta, where e is eccentricity of ellipse and the value of e should lie between 0 and 1. So such type of integrals are called as elliptic integrals. Now elliptic integrals have been categorized into incomplete elliptic integrals and complete elliptic integrals. Now when we say incomplete elliptic integrals, we have incomplete elliptic integral of first kind and incomplete elliptic integral of second kind. Now in the first kind, we have this function of two variables, say phi and k, and we write this as this integral from 0 to phi d theta upon under root of 1 minus k square sine square theta. And in the second kind, it is of the form phi k and then this integral from 0 to phi under root of 1 minus k square sine square theta d theta, and in both these integrals value of k should lie between 0 and 1. And then we have complete elliptic integrals of first and second kind. So now we'll write complete elliptic integral of first kind and second kind. Now in incomplete elliptic integrals, we have two parameters, phi and k. Here we have just one parameter k, and we take this angle phi as pi by 2. So we write this elliptic integral as fk, and it will be this integral from 0 to pi by 2 d theta upon under root of 1 minus k square sine square theta. And for the second kind, we can write this as fk equals this integral from 0 to pi by 2 into under root of 1 minus k square sine square theta d theta. Now these elliptic integrals, they can be changed into many other forms, including those in terms of rational functions. But for this video, we'll limit ourselves to these forms. Now we know elliptic integrals, they cannot be solved analytically. Then how do we solve them? We solve these elliptic integrals using series expansion. So what we'll do is, we'll take up both the complete elliptic integrals and we'll try and solve them. And then using that solution, we'll try and write a formula for arc length of an ellipse. We'll begin with solving complete elliptic integral of first kind. So now we'll solve complete elliptic integral of first kind. Complete elliptic integral of first kind is expressed as fk, and it will be this integral from 0 to pi by 2 d theta upon under root of 1 minus k square sine square theta, where the value of k lies between 0 and 1. Now what we'll do is, we'll write this as this integral from 0 to pi by 2 1 minus k square sine square theta to the power minus 1 by 2 into d theta. Now we'll use binomial expansion of 1 minus k square sine square theta to the power minus 1 by 2. Now we can write this as this integral from 0 to pi by 2, and then this summation m varies from 0 to infinite. Since this is negative and fractional power, this expansion will go up to infinite terms, and then it will be minus 1 by 2 cm minus 1 to the power m k to the power 2m into sine to the power 2m theta d theta. Now we can write this as this summation m varies from 0 to infinite minus 1 by 2 cm minus 1 to the power m k to the power 2m, and then this integral from 0 to pi by 2 sine to the power 2m theta d theta. Now first we'll simplify this expression, which is minus 1 by 2 cm using gamma function. Now NCM is factorial n factorial m factorial n minus n. Now we know that factorial n is gamma n plus 1. So we can write this as this gamma 1 by 2 upon, we'll write this factorial m as factorial m itself, and here it will be gamma 1 by 2 minus m. So we'll write this minus 1 by 2 cm as gamma half upon factorial m gamma 1 by 2 minus m. And then we'll come to this integral part. We'll solve this integral part using beta function. Now we know that beta function is this integral from 0 to pi by 2 cos to the power 2 alpha minus 1 theta into sine to the power 2 beta minus 1 theta d theta. Now this is equal to gamma alpha into gamma beta upon gamma alpha plus beta, and basically we have this 2 times, so we'll write this 2 here. So this cos 2 alpha minus 1 theta into sine 2 beta minus 1 theta d theta, this integral from 0 to pi by 2 will be equal to gamma alpha into gamma beta upon 2 times gamma alpha plus beta. Now we need to find integral of sine to the power 2m theta. So what we'll do is we'll replace alpha with 1 by 2 and beta with m plus 1 by 2. So if we put alpha as 1 by 2, it will be cos to the power 0, which is 1, and here it will be sine to the power 2m theta. So value of this integral from 0 to pi by 2 sine to the power 2m theta d theta, it will be equal to gamma half into gamma m plus 1 by 2 upon 2 times gamma m plus 1, and gamma m plus 1 is nothing but factorial m. So it will be this gamma half into gamma m plus 1 by 2 divided by 2 into factorial m. Now we'll put the value of 1 by 2 cm and this integral in this equation. So we can write this fk as this summation m varies from 0 to infinite minus 1 to the power m, and then minus 1 by 2 cm, it will be gamma half upon factorial m gamma half minus m, and then this integral sine to the power 2m theta, it will be equal to gamma half gamma m plus 1 by 2, and this is 2 into factorial m into k to the power 2m. Now we already know gamma half is under root pi, so this gamma half square will be simply pi. So we can write this as this summation m varies from 0 to infinite minus 1 to the power m pi gamma m plus 1 by 2 into k to the power 2m upon 2 times factorial m square into gamma 1 by 2 minus m. Now there is this one result in gamma functions which we need at this point of time, and the result is gamma z into gamma 1 minus z, it is equal to pi upon sine pi z. Now we'll use this result to simplify this gamma expression. Now we can write gamma 1 by 2 plus m into gamma, and here it is 1 minus z. So it will be this 1 by 2 minus m, and it will be equal to pi upon n sine pi, and here z is m plus 1 by 2. So what we'll do is we'll put the value of gamma half minus m, then we can write this fk as this summation m varies from 0 to infinite minus 1 to the power m into pi. Now here, if we put this expression, then it will be this sine pi m plus 1 by 2 into this gamma m plus 1 by 2 whole square k to the power 2m upon 2 times factorial m square into pi. Now this pi and pi, it will cancel. Now if we look at this sine m pi plus pi by 2, so this sine m pi plus pi by 2, it will be minus 1 to the power m into sine pi by 2, and sine pi by 2 is 1. So it will be this minus 1 to the power m. Now minus 1 to the power m into minus 1 to the power m, it will be minus 1 to the power 2m. Basically, it will be simply 1. So we can write this fk as this summation m varies from 0 to infinite. Now this is 1, and here we have gamma m plus 1 by 2 whole square into k to the power 2m upon 2 times factorial m square. Now here we need one more result from gamma functions, and the result is 2 to the power m gamma half plus m upon under root pi, it is equal to this double factorial 2m minus 1. Now this double factorial is not factorial of 2m minus 1. Double factorial simply means it is product of all the odd numbers 1, 3, 5 up to 2m minus 1. So the result is we can write this gamma 1 by 2 plus m as under root pi upon 2 to the power m into double factorial 2m minus 1. Now if we put this here, we can write this as fk equals this summation m varies from 0 to infinite, and here it will be this under root pi into double factorial 2m minus 1 upon 2 to the power m, and then into factorial m whole square, and we also have this 1 by 2 into k to the power of 2m. Now this under root pi square is pi by 2, so we can write this as pi by 2 into this summation m varies from 0 to infinite, and this is double factorial 2m minus 1, and the denominator, if we look at this is 2 to the power m into factorial m, which is 1 into 2 into 3 up to m, and if we multiply everything with 2, then will be this 2, 4, 6 up to 2m, which is basically double factorial of 2m. That means we are talking about product of all the even numbers in from 2 to 2m, and this square into k to the power 2m. And this is the solution of elliptic integral of first kind. We can write it in expanded form also. So we can write this fk, which actually is this integral from 0 to pi by 2 d theta upon under root of 1 minus k square sine square theta. It will be equal to pi by 2. Now if we put m as 0, then this is 1 and this is 1 and k to the power 0 is 1. So it will be this 1 and then plus. Now if m is 1, Here this is factorial 1. Factorial 1 is 1 and here it is factorial 2. So it will be this 1 by 2 square and then into k square plus. Now if we take m as 2, then this is double factorial 3 and double factorial 3 is 1 into 3 upon, and this is double factorial 4 which is 2 into 4 square into k to the power 4, and then this series will continue up to infinite. So this is how we solve complete elliptic integral of the first kind. Now we'll solve complete elliptic integral of the second kind. Now for the second kind, we can write this fk as this integral from 0 to pi by 2 under root of 1 minus k square sine squared theta d theta, where the value of k will lie between 0 and 1. Now again we write this as fk and then this integral from 0 to pi by 2 1 minus k square sine square theta to the power 1 by 2 d theta, and we'll write it in binomial expansion form. So we can write this as fk equals this integral from 0 to pi by 2, this summation m varies from 0 to infinite 1 by 2 cm minus 1 to the power m k to the power 2m into sine to the power 2m theta d theta, and we can rewrite this as this summation m varies from 0 to infinite 1 by 2 cm minus 1 to the power m k to the power 2m, and then this integral from 0 to pi by 2 sine to the power 2m theta d theta. Now we'll write this expression in terms of gamma function. Now first we'll simplify this, which is 1 by 2 cm. Now this is factorial 1 by 2 upon factorial m and then factorial 1 by 2 minus m, which is gamma 3 by 2 upon factorial m, and this is gamma 3 by 2 minus n. Now we know that gamma n plus 1 is factorial n, which is n into gamma n minus 1. So we can write this as 1 by 2 into gamma half, and here it will be factorial m gamma 3 by 2 minus n. Now we'll find value of this integral, and for this again we'll use beta function. Now we know that this integral from 0 to pi by 2 cos to the power 2 alpha minus 1 theta into sine 2 beta minus 1 theta d theta, it will be equal to gamma alpha into gamma beta upon 2 alpha plus beta, and here again we'll put alpha as 1 by 2 and beta as m plus 1 by 2. So value of this integral from 0 to pi by 2 sine to the power 2m theta d theta, it will be equal to gamma half into gamma m plus 1 by 2 upon 2 times gamma m plus 1, and gamma m plus 1 is simply factorial m. So we write this as gamma half into gamma m plus 1 by 2 upon 2 into factorial m. Now we'll put the value of 1 by 2 cm and this integral pi by 2 sine to the power m theta d theta. So now we can write this fk as this summation m varies from 0 to infinite, and here this is 1 by 2 gamma half upon factorial m and then gamma 3 by 2 minus m into this minus 1 to the power m and then this gamma half gamma n plus 1 by 2 upon 2 into factorial m. Now we know that gamma half is under root pi. So this gamma half square will be simply pi. So we can write this as this summation m varies from 0 to infinite. Now this is pi, and here we have 2 into 2 4 into factorial m square minus 1 to the power m, and this is gamma n plus 1 by 2, and we'll write gamma 3 by 2 minus m as 1 by 2 minus m into gamma 1 by 2 minus m into k to the power 2m. Now we are going to use the same result which we have used for elliptic integral of first kind, and which is gamma z into gamma 1 minus z, it is equal to pi upon sine pi z. So we can write gamma half plus m into gamma half minus m, it will be equal to pi, and then here it will be sine m pi plus pi by 2. Now sine m pi plus pi by 2 is minus 1 to the power m. So from here we can write gamma 1 by 2 minus m is this pi upon minus 1 to the power m into gamma 1 by 2 plus m. Now we'll put it here. So now we can write this fk as this summation m varies from 0 to infinite pi by 4 into m square into now minus 1 to the power m, and here we have 1 by 2 minus m, and we can write gamma half minus m as pi upon minus 1 to the power m gamma 1 by 2 plus m, and we also have gamma n plus 1 by 2 previously also, so will be this square into k to the power 2m. Now this pi and pi will cancel, and minus 1 to the power 2m is 1. So we can write this fk as this summation m varies from 0 to infinite, and here it will be gamma 1 by 2 plus m whole square into k to the power 2m upon 4 times factorial m square, and this is 1 minus 2m by 2. So here it will be this 2. So basically this fk now is this summation m varies from 0 to infinite gamma half plus m whole square k to the power 2m upon 2 into 1 minus 2m into factorial m square. Now here again we'll use result from gamma function, and we know that gamma 1 by 2 plus m into 2 to the power m upon under root pi, this is equal to double factorial 2m minus 1, where this double factorial is not factorial of factorial, but it is product of all the odd numbers from 1 to 2m minus 1. So now we can write this fk as this summation m varies from 0 to infinite, and here it will be this 2m minus 1 double factorial square into this under root pi square, which is pi, upon 2 into 1 minus 2m, and then we can write this as 2 to the power m into factorial m square k to the power 2m. Now 2 to the power m into factorial m is basically 2 to the power m into 1 into 2 into 3 up to m, which is 2 into 4 up to 2m, and basically which is product of all the even numbers from 1 to 2m. So we can write this as double factorial of 2m. So now we can write this series as fk equals this summation m varies from 0 to infinite pi by 2 into, and this is double factorial of 2m minus 1 upon double factorial of 2m whole square into k to the power 2m upon 1 minus 2m. Now basically we can write solution to this complete elliptic integral of the second kind, which is this integral from 0 to pi by 2 under root of 1 minus k square sine square theta d theta as this summation m varies from 0 to infinite pi by 2 into this double factorial of 2m minus 1 upon double factorial of 2m whole square into e to the power 2m upon 1 minus 2m, where the value of k should lie between 0 and 1. Now if we want, we can write it in expanded form also. So in the expanded form, we can write this complete integral of second kind as under root of 1 minus k square sine square theta d theta as, now this is pi by 2. Now if we put k as 0, this is 1, k to the power 0 is 1, so it will be this 1, and then if we take m as 1, we'll get this as factorial 1, which is 1, and here it is factorial 2, so it will be this 1 by 2, and then k square upon minus 1, so it will be this minus 1 by 2 square into k square. Now if we take m as 2, then it will be this minus, and then this is double factorial 3, and double factorial 3 is 1 into 3, and here it is double factorial 4, which is 2 into 4 whole square, and this is k to the power 4 upon, now if we put m as 2, we'll get this as minus 3. We have already taken this minus, so it will be this 3, and this series will continue up to infinite. Now we'll come back to the point from where we have started. We know that perimeter of an ellipse, it is given by 4a into this integral from 0 to pi by 2 into under root of 1 minus e square sine square theta d theta. And once we know the result of elliptic integral of second kind, then we can write this formula as 4a into this summation m varies from 0 to infinite pi by 2 into double factorial of 2m minus 1 upon double factorial of 2m whole square e to the power 2m upon 1 minus 2m, and that is the formula for perimeter of an ellipse.